Okay, change of topics. So for the rest of the week, I want to tell you about Kähler metrics and Ricci curvature of Kähler metrics and prescribing the Ricci curvature of a Kähler manifold, so the solution of the Calabi conjecture. And if I have a little bit of time left at the end, then so this thing that Donaldson did about the positive Kähler-Einstein problem, at least some of that. So I guess in the syllabus there was supposed to be 2 lectures, but I'm going to squeeze them into one. So I guess we already had a definition of a Kähler manifold, but not in a form that's necessarily very enlightening. So I'm just going to recall that and then try to clarify that and say what has to do with Riemannian geometry. Okay, so the definition I gave was that if you have a complex manifold, so that could be compact or non-compact. So then this is called Kähler. If it has a Kähler form, and the Kähler form, by definition, is a 1-1 form. Omega. So I tend to forget to say that, but it's kind of important. So the way I defined 1-1 forms on Cn, those are just complex valued forms, and I want my Kähler form to be real. So I want it actually to be equal to its complex conjugate. And the most importantly, it's closed. So it's a key condition. It's a closed form. And now you actually want to go ahead and relate that to Riemannian geometry. So you want to characterize Kähler manifolds as a particular class of Riemannian manifolds, whose Riemannian metric satisfies extra conditions. So you want to relate this 1-1 form to Riemannian metric. So if using the complex structure. So that's just a piece of linear algebra, but it's a pretty annoying piece of linear algebra. So there's various ways of doing that. I'm going to do it fairly explicitly. So there's so there's 2 things you need to check. The first one is that there's a canonical identification between, so that's just pointwise on Cn. So you have 1-1 forms on Cn that are real, so omega is equal to omega bar. And there's a 1-to-1 correspondence, a linear map to symmetric bilinear forms on Rn. So inner products on Rn, not necessarily positive, but symmetric bilinear forms, so sim squared Rn, that are compatible with a complex structure in a certain way, so that G of Ju Jv is equal to G of Uv. And J is the complex structure on Cn, so that's multiplication by I viewed as a real matrix, as a real endomorphism. It's R2n cross 2n. R2n. So it's symmetric bilinear forms on R2n that are invariant under multiplication by I, so that multiplication by I is an orthogonal map. And so the second fact is that omega is positive as a 1-1 form. If and only if the associated symmetric bilinear form is positive as a bilinear form. So the slick way to explain the correspondence is to say that you just take G of uv to be omega of u and jv. So that's a slick explanation. But it's not particularly illuminating. So it's better to write, maybe if you see that for the very first time, it's better to write out what happens in coordinates to these matrices. And then to convince yourself that this is actually the same thing as the coordinate-free version. So in coordinates, what happens is that so you start with omega. That's your 1-1 form. So by definition, you can expand that as a sum hjk dzj wedge dzk bar. This is just what it means for the thing to be 1-1, and hjk is a complex matrix. But now we're assuming that the thing is actually real. Omega is equal to omega bar. So take a bar over the whole thing. The bar goes here and there, and over the hjk. And then you want to bring that back to the original form, but then you have to switch the j and k's, but you also have to switch the order of the factors because this has become a z bar and this has become a z. So basically that's equivalent to saying that hjk bar is minus hkj. So this matrix is actually skew Hermitian. We prefer Hermitian matrices over skew Hermitian ones, but we can fix that by multiplying by I, and that's the same as this multiplication by j over here. Then we can write h as I times g, where g is going to be Hermitian. And then we just view this Hermitian n by n complex matrix as a 2n by 2n symmetric real matrix. And so what that means concretely is that we replace the jkth entry of G with a 2 by 2 real matrix. There's a normalization here. So to get that right, so take the real part of gjk, the imaginary part of gjk, minus the imaginary part of gjk, and the real part of gjk. Right, so you're replacing each of the complex entries by a real entry, and this is this corresponds to coordinate vector partial x j, this row. This is partial yj, and this is column that corresponds to partial xk, and this one corresponds to partial yk, and that's your g. So in that way you see that the if you care about the flat metric in Euclidean space, then the Kähler form is I over 2 times the sum dzj wedge dzj bar. So this matrix capital G is just 1/2 times the identity, and then under this correspondence that just goes to the identity matrix on R2n. So the coefficients of the flat metric. And once you have this, so once you've rewritten your 1-1 form as a Riemannian metric, then there's various ways of characterizing the Kähler condition in terms of the Riemannian metric. So usually if you look in a book, there's like a list of 7 equivalent conditions, all equivalent to the Kähler condition. It's just that 2 or 3 of them are useful and the other ones maybe not so much. So So the first one would be to say we have a Riemannian manifold. So an even dimensional Riemannian manifold with a parallel complex structure. Complex structure J. It's an endomorphism of the tangent bundle. J squared is minus the identity. So that this J is parallel with respect to the Levi-Civita connection. So that's a Riemannian definition. So it's actually equivalent to Kähler. So the interesting thing is you only need the endomorphism J. Once you know that it's parallel with respect to the Riemannian metric, you actually get that this automatically defines an integral complex structure. So there's an underlying structure with holomorphic charts and holomorphic transition functions. Some equivalent way of saying that is that we have a Riemannian manifold M2n G, whose holonomy is contained in the unitary group. Because the unitary group in n complex dimension is the group of all isometries of R2n that commute with a complex structure, and then the holonomy principle tells you that this complex structure that's being invariant, it's being preserved by the holonomy group at a point, actually has to extend as a parallel tensor field everywhere, and the converse is kind of obvious. This is equivalent to the definition of Kähler over there is not particularly easy to see. So there's another characterization that's more complex analytic, and that's kind of more clear why that would be equivalent to that definition. So that's a statement that locally you can construct the metric from one scalar function. It's called the Kähler potential. So the statement is that, so equivalent data would be a complex manifold M together with an open cover. So it's an open cover. And on each of the patches of the cover, you have a real valued function phi alpha. So that's those guys are going to be called the local potentials of the Kähler metric. Such that what do you need? So IDD bar phi alpha is a positive 1-1 form on each patch. And these guys actually glue up as a global 1-1 form. So IDD bar alpha, phi alpha, is equal to IDD bar phi beta on the overlaps. So that's so for me that's just if I think about Kähler manifolds, this is in one of those two ways usually. This one being sort of more suitable for computations if you want to compute examples, because it's really easy to work with these potentials, and it's really helpful to, if you're actually able to derive a Riemannian metric just from a scalar valued function locally. So that's make computations very easy. So I'm going to show you why the second condition is actually equivalent to the Kähler condition that I first wrote down. So that's not particularly hard. I mean, clearly, if you have data like this, then these guys, these IDD bar phi alphas, are going to glue up to a global real valued 1-1 form, which is positive definite everywhere, and it's obviously closed. So the question is, why can I go the other way? Why can I find a local potential? So that's the real question. So we're assuming that we have a Kähler form, so that's a globally closed form. But the closed form is locally exact by the Poincare lemma. So locally, I can write the thing as d beta. Beta is a real 1 form. What I always do in complex manifolds, I have a real 1 form. I can split it up into its 1, 0, and 0, 1 parts. Omega sits here. That's in the 1, 1 forms. I have del going up here, del bar going up there. Del goes here, del bar goes there. And d equals del plus del bar. So the sum of all of these guys has to be the Kähler form, but the Kähler form is a 1, 1 form, so it doesn't have any 0, 2 components, and it doesn't have any 2, 0 components. So actually, there's a 0 here and a 0 there. So omega being 1, 1 is equivalent to the fact that del beta 1, 0 is equal to 0, and del bar beta 0, 1 is equal to 0. And then, the fact that I can take beta to be real valued, which came from the fact that omega was assumed to be real valued. That just means that, this has to, they have to be complex conjugates of each other. So it's just saying that beta 1, 0 is actually beta 0, 1 bar. So I really only have to look at one of these guys. So convention, like 0, 1 form is better than 1, 0 forms. Del bar is better than del. So then you have 0, 1 form, which is del bar closed. Another thing is that there's a version of the Poincare lemma for del bar that tells you if you're on a ball in Cn or on a polydisc in Cn, sufficiently small open set in Cn, then if you have something that's del bar closed, it's actually del bar of something in 1 degree less, and 1 degree less meaning functions. The del bar coming up here, and there's going to be some complex valued function, so that del bar psi is equal to beta 0, 1. And this one exercise I gave you last Friday contains a proof of this, Poincare lemma for del bar. It's not terribly hard. It's basically just Cauchy integral formula in one variable, sort of applied in a smart way. And then you're almost there. So this tells you that omega is del beta 0, 1 plus del beta 0, 1 bar. So this is del bar psi plus del bar psi bar. So the bar goes separately on the two operators, and then you have to commute them. So this is IDD bar of 2 times the imaginary part of psi. And this is going to be your local potential phi. So the point is you're covering your manifold by small open sets that are so small that the usual Poincare lemma for D holds on that set, and also that the del bar Poincare lemma holds on that set. And that's, for that it's enough that your patches are, isomorphic to the unit ball in Cn, something like that. There's an interesting structure that comes up here. So if you think about it, locally you're able to write your metric as del bar of some function, and you're requiring that the del bars of these functions coincide on overlaps. So the question, the phi's don't have to coincide on overlaps, but the del bars are the same. So that sort of motivates looking at functions whose del bar is 0. So it's an interesting class of functions. It's purely local, so I can assume that I'm on some open set in Cn. Have a real valued function on U, and then I say that phi is pluriharmonic by definition, if and only if del bar phi is identically 0, and then that's actually equivalent to requiring that the restriction of phi to every complex line or to every complex curve is harmonic. for all complex lines L and Cn, U restricted to the piece of the line that's inside U, capital U is Fi, is harmonic. So if in the usual sense of harmonic functions on C, del bar in one complex variable is just a Laplacian. So these local potentials for a Kähler metric differ by a pluriharmonic function on the overlaps, and then it's sort of interest to know, how I can get my hands on a pluriharmonic function, and if there's a way of classifying all pluriharmonic functions, and that's actually pretty easy. So it turns out that a pluriharmonic function, at least if your domain is sufficiently small, is exactly the same thing as the real part of a holomorphic function. So basically these potentials differ by real parts of holomorphic functions if you make the patches small enough. So I'm going to prove that. It's a little proposition. So at least if you assume that your domain is simply connected, then it's going to be true that phi is pluriharmonic if and only if phi is the real part of f, where f is holomorphic. Yep.
Is there a notion of harmonic functions for Cn, or this is exactly the notion of harmonic functions?
No, it's much stronger than harmonic. I mean, pluriharmonic implies harmonic on Cn. It's kind of clear because real and imaginary part of a holomorphic function are harmonic. Or another way to see this is that if you take, you have dd bar phi. And if you take the trace of that, meaning you contract that with a Kähler form, then this is actually just 1/2 times the Laplacian of phi. So this is true on any Kähler manifold. If omega is a Kähler form, then if you take dd bar of any function, wedge it together with the n minus first power of the Kähler form, that gives you a volume form, and divide by the volume form of the Kähler metric, then that's just the Laplacian of that function with respect to the Riemannian metric associated with that Kähler form. So that's true on any Kähler manifold. So this tells you that a pluriharmonic function is harmonic with respect to any Kähler metric. Right, so pluriharmonic is a definition that only depends on the complex structure. Harmonic is a definition that depends on the metric, but if your metric is actually Kähler with respect to the complex structure, then pluriharmonic implies harmonic by this argument, and that's this is a definition, and for this you need to know a little bit. Most convenient way of seeing this is to use another equivalent characterization of Kähler metrics that I didn't write down. So this means that pluriharmonic implies harmonic in Kähler manifolds. But the definition here that the restriction to each complex line is harmonic, that's not a metric condition, because in, complex line is like a piece of a Riemann surface, so I'm fixing a conformal structure, and the Laplacian in complex dimension 1 is conformally invariant. So to say what it means to be harmonic on a complex curve is kind of, the Laplacian on a Riemann surface is sort of independent of the conformal metric that you put on your Riemann surface, used to define the Laplacian. Okay. One direction is very easy. So that's just the statement that real part of a holomorphic function is basically f plus f bar. And so this is del of del bar f minus del bar of del bar f bar. And del bar f is 0. So for the other direction, it's sort of convenient to use this operator, dc. That's I times del bar minus del. So I mentioned that once before. So I mean, the advantage of using d and dc over del and del bar is that those are real operators. So d of a real form is real and dc of a real form is real. And then it's just going to be true that ddc is 2i del bar. So if phi is pluriharmonic, then this means that ddc phi is 0. So this is a closed one form. Now I'm assuming that I'm working on the open set, which is simply connected, or anyway, whose first Betti number is 0, meaning that the closed one form is necessarily exact on that open set. And so I can get a primitive for my one form by integrating along paths. And a priori, the integral only depends, because the one form is closed, the integral only depends on the homotopy class of the path. And then you still have a period issue in general if my domain is not simply connected. The different homotopy classes of paths could sort of change my integral by by a constant. So if the domain is simply connected, that doesn't happen. So dc phi can actually be written as d psi, maybe. And then this is a harmonic conjugate. So if you write out what I'm doing here in complex dimension 1 in the plane, then that's just a construction of harmonic conjugates. This condition here, if you rewrite that in terms of del and del bar, this is just saying that del bar psi is I times del bar phi. And then del bar of phi plus I times psi is 0. So that's a holomorphic function. So one of the exercises yesterday, when the one about finding a good local trivialization for a given Hermitian line bundle, that's implicitly about pluriharmonic functions. So saying, you take your Hermitian metric, write it as e to the minus phi. You make a Taylor expansion, so you write phi as a constant plus linear terms plus quadratic terms plus higher order. And then you realize, well, constant terms are sort of pluriharmonic anyway. Del L bar goes to 0. Linear functions are pluriharmonic because every real linear function on Cn is the real part of a complex linear function. And then for quadratic polynomials, they're split up. So some quadratic polynomials are not pluriharmonic and some are. And the ones that are not pluriharmonic give you the curvature of your Hermitian metric, and the ones that are not pluriharmonic just go away. And you can sort of take the pluriharmonic parts and write them as a real part of some holomorphic function, and then you change your trivialization by the exponential of that holomorphic function. So this is sort of one slick way of doing that exercise. Okay. Just give you a couple of examples of Kähler manifolds. But this, at this point, it's not terribly exciting anymore. So all manifolds with positive holomorphic line bundles are Kähler. So by definition. For example, projective space itself, so Pn, and you're taking the curvature form of this canonical metric on OPn of 1. So if you view that as a Kähler form, then you would usually call that the Fubini-Studi metric. This particular curvature form that I constructed last week, a lot of symmetry. So if you have this somewhat obvious point here that, on one hand, if you have a complex manifold with a positive line bundle, then omega h is just a Kähler form by definition of what it means to be positive. So curvature form, if your line bundle is a Kähler form. But then, on the other hand, if the manifold is compact at least, then by Kodaira embedding, if I pass to sufficiently high tensor power, I can also, I get an embedding into projective space, so I can pull back the Fubini-Studi metric under this holomorphic embedding, and positivity is preserved under holomorphic embeddings. So I can pull back the Fubini-Studi metric, and that's going to give me a Kähler form also. So at least if M is compact. If I take the Kodaira map phi sub L to the K from M to some huge projective space, then phi L sub L to the K star of the Fubini-Studi metric is a Kähler form. Not usually the same that you started with here. It's sort of an interesting exercise to compare the two, like the curvature form of your line bundle and the pullback of the Fubini-Studi metric on Pn under these embeddings. So if you do that here, that leads you to the study of what's called the Bergman kernel of holomorphic line bundles. So that's something that people tend to study a lot these days. They're the same on CPN, obviously. But yeah, the definition of a positive holomorphic line bundle doesn't require the manifold to be compact. So, Cn is a Kähler manifold, and every affine manifold is a Kähler manifold. And then, submanifolds of affine and projective space are Kähler. That's pretty much all the examples you need. There are a couple more. Products of Kähler manifolds are Kähler. It's kind of clear. quotients by free holomorphic plus isometric group actions are scalar. So you only need the group action to be holomorphic if you want to get a complex manifold on the quotient, but you do need it to be isometric if you want the quotient to inherit a scalar structure again. So in 2 minutes I'm going to give you an example of a holomorphic group action which is not isometric, so that the quotient is no longer scalar. So it's sort of the obvious condition that you would put here, but it's actually necessary in general. So for example, tori are scalar, even though they're, but even though they're usually not projective if the dimension is at least 2, so they're not submanifolds of projective space, but just, because I can write them as equations of Euclidean space, they're sort of obviously scalar. So every Riemann surface is a priori scalar. So even without knowing that the surface can be embedded into projective or affine space, so let's just, you take a conformal metric G. Construct your 1-1 form, so that's just going to be G of, you multiply by I in the first coordinate only, and then that's a 2 form, and it's got to be closed because Riemann surfaces don't have any 3 forms. And then there's this one example of a non-scalar manifold that I want to give. So that was on the homework yesterday. So if you take C2 minus the origin, and you mod it out by the infinite cyclic group generated by, just dilation by 2. So you're identifying x and 2x and 4x and 1/2 x in C2 minus the origin. So that's a compact complex surface that's not scalar. So you see I start with something that's scalar, and I mod out by a discrete free group of holomorphic transformations that are pretty close to being isometries. I mean, they're dilations. Don't do anything weird, it's just dilations, but they're not isometries. So they don't preserve the full scalar structure, only up to scalars. And actually on the quotient, you're not going to be able to find any scalar metric, and it's still an exercise for you. And there are sort of more sophisticated examples. That sort of flavor. You can derive all sorts of obstructions to a complex manifold being scalar using Hodge theory, algebraic topology. And for all of these obstructions, you can cook up sufficiently sophisticated examples that aren't scalar but pass all the tests. So you can push that pretty far. But that's not scalar. I mean, this guy here is not scalar for a pretty obvious reason. So then I'm going to state 3 facts. So 3 theorems that hold on Kähler manifolds and that sort of explain why people like them. So let's I'm going to prove at least one of those. So Kähler miracles. The first 2 have to do with Hodge theory on the manifold. So one of them we already saw, that's the Dellel-Bar lemma. But the third one is sort of the most miraculous one of all, so that's what relates the Kähler condition to Ricci curvature. That if you compute the Ricci curvature of the Riemannian metric associated with the Kähler form, that has an extremely simple expression in holomorphic coordinates, so that you can actually, prescribe the Ricci curvature of a Kähler manifold by solving a PDE. So for Kähler manifolds, you have almost complete control about what the Ricci tensors can possibly be. So they're a great source of examples for this sort of regularity theory, for example, if you're interested in manifolds with bounded Ricci curvature, Einstein manifolds. It's going to be the third point. The first point is the Dellel-Bar lemma. So that's the global Dellel-Bar. Already saw the local Dellel-Bar. So that says that if M is compact Kähler, and if eta is an exact real 1-1 form on M, then eta is actually equal to IDD bar phi for some real value function phi that's globally defined. So we already used that once implicitly, more or less, to say that every 1-1 representative of the Chern class of a line bundle can actually be realized as a curvature form of a Hermitian metric on that line bundle. I mean, it's true for complex 1-1 forms also, and then phi is going to be complex. Okay, there's no real content here. If you have the complex version, you get the real version because I del bar is a real operator that commutes with complex conjugation. It's just like real functions better than complex ones. So let me prove that. So the proof is pretty much the same as the one we did locally in the beginning. So I'm writing eta as d beta. Beta is a real 1 form. I know that del of beta 1, 0 and del bar of beta 0, 1 are 0, and the 2 pieces are complex conjugates of each other. So beta 1, 0 is beta 0, 1 bar. And now, of course, you have a little problem. So you have this 0, 1 form, which is del bar closed, but you don't have the Poincare lemma available because now you're working globally on a compact manifold. So a priori, you have no idea whether that's actually del bar of something or not. But, from Hodge theory, you know that the obstructions are given by harmonic forms, and harmonic forms on the Kähler manifold are extremely special. So I guess there's various ways how you could finish the proof. So the one I like best is to say, so you solve the equation del bar star del bar c equal to del bar star beta 0, 1. So this operator here, I'm taking the adjoint with respect to a Kähler metric. Okay, so this operator here is basically Laplacian. So it's a second order elliptic operator that kills constants. This guy here, because it's d bar star of something, is perpendicular to the constants. So it's actually possible to solve this thing. So by the Fredholm alternative, uniquely up to constants. So it's basically a Laplace equation. So then consider Xi, so this is d bar psi minus beta 0, 1. So that's a 1, 0 form, and that's the guy that we would like to be 0. You know, if the Poincare lemma was true, we could actually arrange that this is 0, sort of right off the bat. It's not going to be 0 in general, but it's a harmonic form. So notice d bar Xi is equal to 0, but also d bar star Xi is equal to 0. That's sort of clear. I'm taking d bar twice here, and by assumption this guy was d bar closed, and this condition here is just the PDE that I solved up here. So that's just a Laplace equation that I solved. So by definition, what this is saying is that Xi is d bar harmonic and that's of the second Kähler miracle. But this is the same thing as saying that Xi is del harmonic. So the same equation, I mean, it's del Xi is 0 and del star Xi is 0. So what this means actually is that Xi is necessarily the conjugate of a holomorphic 1 form. So i.e. Xi bar is a holomorphic 1 form. And this just tells you that if you would like Xi to be 0, a priori it doesn't have any reason to be 0, but it's actually something that's del bar closed by some sort of Hodge theory miracle on Kähler manifolds. So if you take, you want to take another del here to get back to your original form eta. So you have this Xi thing here, which is non-zero, but it's del closed. So if the del hits that, then it goes away. Okay, second miracle. This is the thing that I used there. So on a Kähler manifold, it's true. The Hodge theory, it's extremely simple. The theory of harmonic forms. It's true that if you form the Laplacian associated with del bar, this is 1/2 of the Laplace-Beltrami operator. It's actually equal to the Laplacian that you form using the operator del. Right, and the Kähler condition enters here through these adjoints. That's where I use the metric. Del and del bar are different in terms of the complex structure, and then I form adjoints using the metric, and I get these Laplace-Beltrami type operators. And the big miracle is that they're actually the same. So this has all sorts of consequences. One of them was over there. That implies these decompositions that H1MC splits up as H10M plus H10M bar. H10 is the space of holomorphic 1 forms. You have H20M plus H11MC plus H20 to 0 m bar, actually. So you have the space of holomorphic two forms, its complex conjugate, and then there's another piece that's invariant under complex conjugation, so that has a real subspace. And that's the cohomology classes of closed forms of type 1,1. So this is where the cohomology classes of the Kähler forms themselves sit, and this is also where the first Chern classes of holomorphic line bundles sit in this piece, in the complex conjugation invariant subspace of this piece. And you have these interpretations of the remaining pieces in terms of holomorphic forms. And the third miracle, I mean, this is, depending on how you do it, it's more or less unpleasant computation to check that these identities hold. I want to at least write down the third miracle, so it's a Ricci curvature. Which I guess maybe the main reason why so many people in geometric analysis actually care about Kähler manifolds to some extent. So if M is a complex manifold, omega is a Kähler form, then I can make the following construction. So I get a Hermitian metric that I'm going to call H sub omega on the bundle of N0 forms. So that's what's usually called the canonical bundle of the manifold. It's a holomorphic line bundle. So you're taking all forms of type N0, and locally there is only one up to scale. There's dz1, wedge dz2, and so on, wedge dzn. And then you can multiply that by a scalar. So the fiber of this vector bundle is actually a complex line. So it's a holomorphic line bundle. And how do I define my Hermitian metric? So I fix an element of the fiber here, and then I define H sub omega of capital omega. So I have the volume form of my Kähler metric, that's little omega to the n. And this is an N0 form, so I can wedge it together with its complex conjugate, and I get another volume form on the manifold. And to make it real, I put an I to the n squared in front. So that guy here is a positive definite real valued volume form. So the ratio of these two guys is going to be a positive real number unless capital omega is 0, and it's a Hermitian norm. It's homogeneous of degree 2 under multiplication by complex scalars. And then the miracle is that if I take the curvature form of that Hermitian metric, so if I take omega sub h sub omega, and turn that into a symmetric bilinear form using this trick that I multiplied by I in the second variable, then this is the Ricci curvature of the underlying Riemannian metric. So Ricci is a symmetric bilinear form. By inserting this factor of I in the second slot, I turn it into a real 1,1 form. And as such, it's just a curvature form of the canonical line bundle of holomorphic volume forms with respect to that Hermitian metric.
So can you say what is omega sub h?
Yeah. H sub omega is the Hermitian metric on lambda N0 that I cooked up from little omega using this formula. And omega sub h this is the curvature form. So I have a Hermitian metric, and that's the associated curvature form. So this means that if I want to prescribe the Ricci curvature of a Kähler manifold, basically all I have to do is prescribe the volume form. And this is of the content of the Calabi-Yau theorem, that is basically possible in all cases that you expect it should be possible. It comes down to solving the complex Monge-Ampere equation, like the determinant of the complex Hessian of some function equal to some given thing. And I think that's what I'm going to do in the rest of the week to, explain this a little bit more and then show you how to actually prove the Calabi conjecture that the Morgan-Pair equation is always solvable. So in particular, you get obstructions to Ricci flatness. If your KLM metric is supposed to be Ricci flat, you get that the canonical bundle has to have a flat metric. So therefore, the first Chern class of the canonical bundle is trivial in real cohomology. If your complex manifold doesn't satisfy that, there's no way you could find a Ricci flat KLM metric on it. Okay, that's enough for today. Got some more homework too.